introducing me and for inviting me. I feel very honored. I'm a geographer who is doing remote sensing, so maybe my view on the topic might be different than some of yours. Also, the presentation is a rather egocentric view on the topic from which we do in my working group. And maybe you will see why we try to approach biomass and N-uptake monitoring differently. First, motivation, background, why we are doing this kind of research, state of the art. I mean, what is kind of proven in the literature from project. And I would like to give you some insights in case studies we are conducting, and finally give some conclusion and maybe some thoughts for discussion. Yeah, what is the motivation why we are doing this? So we are interested in classical remote sensing approaches for crop type monitoring, but we also would like to know vitality of crops, and I mean with crops also including pastures and meadows. In this talk, the focus will be on nitrogen and biomass, which I think becomes more and more important. But also structural properties like fractional vegetation cover or biogeochemical properties, chlorophyll, carotenoids, lignin. These are of interest to monitor. Yeah. And also the idea always is, as it was mentioned in many talks, that we provide information for decision making and management or for precise agriculture. However, there are some limitations when it comes to proximal and remote sensing from my point of view. The first one might be that a similar signal from the canopy is caused by different stresses. For example, nutrient stress could be a similar signal than water stress, as well as if you have a root pathogen, it might be giving you a similar signal from the leaves compared to water stress. So there are difficulties in the surface properties, especially in grasslands. We have floristic heterogeneity when it comes to pasture systems. And one of the key factors for us in remote sensing, in my opinion, are changing weather conditions. So research objectives are non-destructive determination of crop traits. We are interested in combining structural, spectral crop canopy traits. Even so, in this talk, I may focus more on the structural part. And we also always think about how we can provide fast data acquisition and, in the best case, real time or maybe after a few hours, data analysis for management decisions. This idea is not new. So if you look to the literature, there are airborne images used for management purposes for agricultural applications. The first maybe date back almost 100 years ago. And also when it comes to structural properties, especially in grassland, has a long decadal tradition that plant height, for example, here times ground cover is a very good estimator to forage production, which we actually use nowadays. This kind of approach when it comes to biomass or forage mass, herbage mass monitoring in grasslands. From the background, what usually do we do in remote sensing? This is also not new. We do multiband or hyperspectral, multispectral image acquisition, as it was described here in the 50s. Then we also collect spectral data with field spectral radiometer data for different surfaces. In that case, usually different vegetations or different managed crops. Also, it's not new. There has a long tradition, and the multi-band cameras nowadays, or hyperspectral cameras, look maybe more sophisticated, but actually the idea was there almost 6 decades ago, and really many very brilliant scholars work on those ideas, how to exploit, which I say it's a 1000 nanometer domain from 350 to 1000 nanometers, how we can use this information from the canopy reflectance to derive crop traits. So that this is nothing really new. Maybe our analysis or acquisition methods change, but the idea of chlorophyll absorption or near-infrared reflection are still the same basic. So when it comes to the limitations, and I said that I believe in some areas weather conditions are a key player in limitations for sensing approaches. I would like to show you a fractional cloud cover data for the year 2021. And you see here in the middle somewhere there's Germany, and we are in a class of 62.5 to 75% cloud cover in average in the year. So if we even look to 1 month, you see here again, it's not better, and May is an important month for field crop monitoring, and it's very difficult to get a nice clear sky conditions with low winds. And we have some sites, grassland sites here close to the North Sea, where you see it's even worse, and also here in the middle of Germany, in close to Göttingen, where we also have a field, or we are involved in a field trial of the University of Göttingen. So clouds are a challenging term. So this is just a photo from 2 days ago at the campus Klein-Albendorf of the University of Bonn. Cologne is very close to the University of Bonn, and Cologne does not have an agricultural faculty, so sometimes we are in cooperation. And what you see, this is said to be a sunny day. Yeah, so also you see in the background it's very sunny, but my team with the field spectroradiometer measuring canopies of reflectance are standing in cloud shadows. And these clouds were moving as usual very fast. So it's almost, with the field spectroradiometer, you just wait maybe until there's you are in sunshine, but also this is not perfect condition for a field spectroradiometer data. But this is maybe a very good day for us. So, but it's usually not ideal in terms of, we should have a clear sky conditions. This year, we did not have many very nice blue sky conditions, let's say every week, if you want to monitor crop growth precisely. So that's a problem. Besides, I said the clouds were moving very fast. We have a severe wind strength. Yeah? So the disturbance, the wind is moving the canopy like waves in this growing stage. And of course, this influences the canopy reflectance up to 10 to 15% in the spectrometer. So that's also not ideal. You have too strong conditions. If we fly our UAVs, sometimes we fly for 10, 20 minutes. And in those days, it's almost impossible to find a slot where we have a constant irradiations. Sometimes the drone is in the sun, but the picture it makes is shadowed, or vice versa. So we have a mixture, and for a multi-hyperspectral data acquisition, this is far from being ideal. So that's kind of the motivation why we think that for some regions, it might be a problem to derive nice spectral data from the optical domain for crop trait monitoring, let's say in practical management applications. So what do we have? We know that spectral crop traits are retrievable from the spectra. we know from literature that there are certain absorption and reflection features which are giving or indicating structural or biogeochemical properties. It's well described, for example, from Dar Roberts in a book chapter. So we have those properties. It's widely used for these decades, and it's proven that if you have a good conditions, weather conditions, you can derive nicely some properties. When it comes to what I call, in that case, non-spectral or structural crop traits, we have in situ measurements described by Marshall and Tankerbile. And one is the nitrogen concentration or nitrogen uptake. Usually, we try to derive nitrogen concentration from spectral features. Even so, nitrogen does not have a distinct absorption feature in the spectrum. That's a problem because not all nitrogen is within the chlorophyll. Yeah. So we have spectral predictors for biomass, nitrogen concentration, sowing density, which are used in the literature, but maybe since 10 years, we find more and more paper and work and that we use, which I call 3D data from photogrammetry, laser scanning, or ultrasonic sensors. And those are the non-spectral predictors, which are or could be also used, especially it's well described for crop height or crop volume, sowing density, fractional vegetation cover, especially biomass is working very well, but it is not used for nitrogen concentration and uptake. Yeah? It's no wonder it's a discussion and not all colleagues agree to the idea to use 3D data like point clouds or surface models to use for nitrogen retrieval. So the state of the art from my point of view, what it's done. So for example, terrestrial or mobile laser scanning can be applied on the field level. With UAVs, it's proven that if you create these multi-temporal digital surface models, you can measure with, I would say, an error bar of 3 to 4 centimeter, the height in centimeter in a spatial resolution of also centimeters on the field level. And you can nicely derive continuous data, like here for a grassland experiment in the Eifel region of Western Germany, where we have a very strong cloud cover and you don't care about irradiation or blue sky condition, you just go and derive your structural data workflow, and it seems to work. So that's proven. The numbers which you derive from deriving plant height, for example, you can use plant height as an exponential model. We call it biomass regression models in that case, and plant height slowly in a simple data analysis approach works pretty well in all our applications. So it usually always comes up over on a multi-temporal analysis with an R-square of 0 larger than 0.8. The only classical approach to retrieve similar results are vegetation indices in our studies, which make use of the shortwave infrared bands from higher than 1000 nanometers, especially between 1000 and 1700 nanometers. The traditional 1000 nanometer domain usually does not perform so well for biomass in a robust term, especially if you always want to transfer your findings to a different data set. This was done by laser scanning. We know that it seems to work. And the same approach was done with UAV data, deriving with photogrammetry. structural for motion and multi-view stereopsis approaches the data, and we come up with a similar R-square for the same crop. So it seems to work. Now, knowing that we can use plant height as an estimator for biomass, and in grassland, as I showed at the beginning, the citation from the late 50s, it's known for a long time that if you have kind of a compressed sward height, it's giving you a nice measure for the forage, amount of forage or the amount of biomass. So what we know that the crop surface height is predicting biomass. And from the textbook, and this is, we are geographers, we are no agricultural engineers or plant nutrition scientists or agronomists. We also know, and this is well described, that over time during plant growth, we have a relation between biomass and nitrogen concentration. It's a decreasing function. So the idea is that we first create a model, biomass regression model with crop height, and then we create from biomass and nitrogen regression model to use biomass to model nitrogen concentration. Again, in the data set which we investigated, it worked well. We are feeling supported by the idea at first, and there are some explanation why it could work, because we always work on kind of a field level on canopy scales, and our zonal statistics of the plots are 1 to 3 square meters, yeah, where we average our data, and it seems that on such a scale it will perform, which are in fact are feasible management units if we would like to transfer the idea into practice. This is case study two, which I would like to introduce, which we do in winter wheat. So what you see is here in the first row, it's the crop height derived with a UAV, DJI Phantom 4 RTK drone. Then we have the manual crop height measurements, and we have here nitrogen concentration plotted against fresh, dry, and crop moisture, which to crop moisture I come later. But what we see again is that the crop height can model fresh and dry biomass with a very simple approach. Well, if you plot all your multi-temporal data sets, and you see here when we have conducted the campaigns, for each campaign, we did destructive sampling, weighed the fresh biomass, dried it, and then weighed the dry biomass, and then did the CN analysis in the lab. Also, we see that a manual crop height performs similar, but not as strong as the UAV crop height. And what you see here, for example, with a dry biomass, you see, again, we have this negative function. But what you also see is that, of course, for each date, we have a positive trend in the function with a different inclination of the trend line. Yeah. But this is also well known, and this is what we would like to use in future. Interesting maybe here, just the crop moisture data set. We are also interested in monitoring crop moisture, because if you have an approach which works for both for fresh and dry biomass, then and which obviously it does, you can map the crop moisture content, which is also an aim for that purpose. This is this first case study. This is the trial. We have 5 repetitions. It's 3 nitrogen management strategies and 6 varieties. At the moment, we have not analyzed it separating or investigating each varieties because we still collecting data. We will do that as soon as we have a 3 years data set, and we are currently in the 2nd year, which almost is finished, hopefully. Yeah. But what you see here is that the N-uptake, which is calculated by biomass and N concentration from destructive sampling against plant height of UAV, is giving a number or well R-square. It's still improvable, but it could be an indicator that it performs well. In that case, in this figure, we have not used first a biomass regression model and then from the biomass regression model, a biomass N model. But this is what we're still doing and which is under investigation. If we use our data from 2020, which I showed before, and create a height biomass model for dry biomass, we can now apply the first step, this model from 2020, to see if it's working on data sets from 2021. And this is shown here. We see it's a little too high, so our modeled values are higher than it should be. It does not fit very well to the one-to-one line, but still these are ongoing investigations, and we are still think that's, that we will maybe find solutions to fit this to the model so that we really can provide for those wheat varieties a height-dependent biomass model, which we then can use to model an uptake. Conclusions we see in the literature from, for example, other groups estimating biomass and nitrogen in barley or also in grassland, that for biomass, the 3D features, so they investigated several features like mean crop height, 90 percentile, or maximum crop height, and so forth, are the most important features for the analysis, but still for nitrogen content, the hyperspectral camera in their study gave the best results. So that's still competing, but you need good weather conditions for the spectral camera. So it should be proved if you can produce it in practice from remote sensing under management perspectives. Also for rangelands, we see groups using LiDAR data and UAV hyperspectral data. The integration improved the monitoring results, especially the height difference, or to include the height difference in the analysis was crucial and most important. And we see this in a study from Viljanen as well. If you see the features, the most important features in a machine learning approach for a dry matter yield and fresh matter yield, you see only the excessive green index here is a spectral indice, but you clearly see that the other features are the structural height features, which proved to be most important in the multivariate analysis, which is still ongoing in several groups and provides for the field level monitoring a huge opportunity. Now coming back to nitrogen, this is a figure showing for different growing stages the important absorb or wavelengths for nitrogen concentration in temperate grassland. And what we see is that, of course, it's changing over time, that's clear, but if you sum up with the overall analysis here on the bottom, you see that there are additional important features for nitrogen, which are not only in the 1000 nanometer. So here, if you plot this, we see a typical grass spectra. We see the chlorophyll absorption bands. We see very nicely the water absorption bands of the canopy. And we also see that there are some components which also include nitrogen, amino acids or whatever, or proteins here, which might be of use to improve nitrogen concentration strategies. Yeah, so what is our research goal at the moment? What do we fly? We fly commercial DJI sensors, the RTK and the multispectral. And we additionally fly a UAV lidar with a Mica sense mounted, which is a multispectral camera, including the red edge. So the DJI multispectral is a very similar sensor to the Mica sense. But especially for the moisture content and for the biomass, we developed an own sensor with in a cooperation with the Applied University of Koblenz. This Alex Jenal, this is his work, and we developed a Fournier sphere imaging system, not as a push broom, as a frame sensor, with which we are monitoring biomass, of course, but we also go into the sphere bands where we think we can see water and protein absorption to combine those for the analysis. Yeah, this is my presentation. I think that the machine learning has some advantages when it comes to combined analysis of structural and spectral features. But however, for management purposes, I still believe that structural remote sensing might come up with robust models to estimate biomass and nitrogen concentration, and especially biomass is the most important trait to recommend nitrogen uptake. And with this, I would like to thank all my colleagues, which co-authoring all the papers I showed, and of course my group members, which do this fantastic work. Thank you.